Hello, everybody. In this video, we're going to be talking about the first derivative test. And this does not mean that it's the first of the derivative tests. It means it's a test involving the first derivative. And what are we testing for? Well, this test is testing to find where the local maxima or minima of a function are. So where is our local maximum? Where is the local minimum? We want to find all of those. Okay, so let's take a look. All right, so like I said, what we want to do is identify where we have a local maximum, a local minimum, or other features of the graph. All right, and we want to relate this to the first derivative. Okay, so here we have an example where we have a local maximum. You can see the graph is like a parabola opening downwards. Now, what does that have to do with the first derivative? Well, we can see that to the left of the maximum point here, we can see that the derivative was positive. And to the right of the maximum point, we can see that the derivative is negative. So the derivative has changed sign. It has changed from positive to negative there. Okay? Here's an example where we have a local minimum. Now, and this looks like a parabola opening upwards, right? So there's the local minimum right there. Now, let's look at the derivative. The derivative to the left of the minimum was negative, and to the right of the minimum was positive. So again, the derivative has changed sign. It has changed from negative to positive. Okay, let's look at another example. Here's an example where we have neither a maximum nor a minimum. And you can see what happened here is that the derivative over at this point, before it got to that point was positive, and after that point is positive. And here's another situation. Before we got to that point, it was negative, and after that point, it was negative. So I think what you should be noticing here, is that we're looking, if we want to find maximums or minimums, we're looking for where the first derivative changes sign from positive to negative or negative to positive. If it stays positive or stays negative, you wouldn't expect to find a maximum or a minimum there. Now, one thing I want to point out is that these are all continuous functions, all right? So that may have something to do with our theorem that we'll be looking at next. And that theorem is called the first derivative test. And this is theorem 4.9 if you're using the OpenStax textbook, all right? It says, suppose that c is a critical number of a continuous function f. Like I said, all these are continuous functions. And c is a critical number. Remember what a critical number is. A critical number is a number where the derivative is either equal to 0 or is undefined. In all of these examples, the derivative is equal to 0 there. Right? Now, there are three parts to this first derivative test. Part A says, if f prime changes from positive to negative, that's what happened in this first example here, then f has a local maximum, and that's what we're seeing. That's a maximum. If f prime changes from negative to positive, that's what we're seeing here, then f has a local minimum. Well, look, that's exactly what we're seeing. If f is positive to the left and right, or negative to the left and right, then f has no maximum or minimum, and that's what we're seeing in these examples. So that's the first derivative test. All right, so here we have some exercises, and the exercises ask us to use the first derivative test to find the local minimum and maximum values of f. And we have several functions f down here. Now, you should recognize these functions from the previous video on the increasing-decreasing test. All right, so if you haven't watched that video already, please stop this one, go watch that one, because what we discussed there is very relevant to what we're doing here. Okay, but anyway, let's start with this first function, this polynomial right here. Okay, so here's our function. Now, we want to find the maximums and minimums. We want to use the first derivative test. Okay, so look at the hypotheses. It says, suppose that c is a critical number of a continuous function. Okay, so first of all, is this a continuous function? So think about that for a second. Okay, so you should have deduced that absolutely it is, and the reason is that it is a polynomial. Polynomials are continuous everywhere they're defined. Okay, what does the test say to do next? It says to find the critical numbers, right? We need to find where these critical numbers are. What is a critical number? A critical number is where the derivative is 0 or does not exist. We don't have to worry about the derivative not existing for a polynomial, but we can find where it's equal to 0. So let's compute the derivative of this function, and we're going to set it equal to 0 and solve for x. And just like in the last video, we divided through by 3 and then we factored. So let's do the same thing here. And I see that there are two solutions. So the critical numbers are the values -1 and 3. Okay, and those break up the number line at 2 places. Okay, so what does the first derivative test say to do? It says to look at the sign of f prime. If it changes from positive to negative or negative to positive, what's going on there is going to determine whether these are maximums or minimums. Right, so we're going to look at the sign of f prime. Now, in the last video, we did this. We plugged in a number. I think we plugged in -2 in for f prime. So just plug that in for x and compute this. You get positive 15, so it's a positive number. Plug a number in here, like 0, you get -9. It's a negative number. You don't really need to compute it all the way out. You just need to see what the sign is. Plug in a number over here like 4, and you see if you plug it in here, you get a positive number again. All right? So the sign of f prime is what we're talking about here, and that's what we need to talk about to use the first derivative test. If it changes from positive to negative, and that's exactly what happens at this critical number, then f has a local maximum at that number. Okay, so it changed from positive to negative at -1, so that means that f has a local maximum at -1. And let's see what happened at 3. At 3, it changed from negative to positive. Well, what does that mean? If it changes from negative to positive, that means that f has a local minimum. Now, what we've determined is where the local maxes and minimums are, right? We determined where they occur. But what the question is asking is, what are the local minimum and maximum values? All right, so the values are the values of the function. So that's what I would get if I plugged this number in to the function. Now, don't plug it into the derivative. We're not asking what's the minimum value of f prime. We're asking what the minimum or maximum value of f is. So to find these, what we're going to do is we're going to take these values and plug them in to the function f. Now, when you plug -1 in for x, and I'll let you do that computation on your own here, you'll see you get 9 as the answer. So it has the local maximum, you could say, of 9. That's the maximum value at x equals -1. So we're telling what the maximum value is and where it occurs. For the local minimum, we will plug in 3 in for x and see what we get here. And you see you get -23. So the local minimum value is -23, and it happens at x equals 3. So one thing you do want to distinguish here is the difference between these things, the value of the function and where that value occurs. And we can verify this looks correct by looking at the graph. And so you can see that the maximum over here occurs right here, and it happens at -1, and it has height 9. And we have a local minimum right over here. It occurs at 3, and it has height -23, just as we said. All right, let's go to the next one here. We have this function, and again, we saw that in the last video. So what we have to do is we have to verify that it's a continuous function, well, to use this theorem. And let's see, can you see why that's a continuous function? So think about that. And you should have concluded that yes, of course it's a continuous function because it is a rational function. And rational functions, we learned, are continuous wherever they're defined. They're not necessarily defined everywhere, this one is, but they will be continuous wherever they're defined. Okay, so we're going to look at that function here. Now we need to use the first derivative test. We're going to compute the first derivative. We did this in the last video, and we got this. All right, so we want to find the critical numbers. The critical numbers are where this is 0 or undefined. Right? Now, this one is a rational function, so it could be undefined. So we do have to think about where the denominator might be 0. However, in this particular case, the denominator is always a positive number. It's always bigger than 1 because it's 1 plus something squared. So it will never be equal to 0, so we don't have to worry about that. All we really have to worry about is where the derivative is equal to 0, and that can only happen when the numerator is equal to 0. You can't divide by something non-zero and get something 0. So the only way you can get 0 is if the numerator is 0. Okay, and just like in the last video, we factor this to solve it. And we see there are two solutions. There's x equals 1 and x equals -1. Those are our critical numbers. Okay, so what we're going to do is we're going to investigate how f prime changes sign around these critical numbers. So we draw a horizontal axis and we label these critical numbers here, and we're looking at the sign of f prime. And just like we investigated in the last video, we take a number, say -2, plug it in over here, and if you plug -2 in for x, you see you get a negative answer for f prime, a negative value, right? Plug in a number in here like 0, you get a positive value for f prime. Plug in a number over here like +2, and you get a negative value for f prime. Okay, so at this critical number, f prime changed from negative to positive. What does that mean? Well, if it changes from negative to positive, it has a local minimum. And so we have a local minimum at x equals -1. Now, what is the value of that local minimum? Well, I'll get that by plugging this number into the original function. And if you do that, if you plug -1 into the original function, you get -1 over 2, it's -1/2. So the value of the minimum is -1/2. So f has a local minimum with value -1/2 at x equals -1. And over here we have a critical number. It changes from the f prime changes from positive to negative. So positive to negative means it has a local maximum. And what is that maximum value? Plug 1 in for x. 1 over 1 plus 1, that's 1/2. So f has a local maximum with value 1/2 at x equals 1. And this answers the question. And let's just go look at the picture to see if this looks right. And okay, here's our graph, and we see that it has a local minimum at -1 right there, and the value is -1/2. We have a local maximum right here at 1, and the value is, sure enough, 1/2. And finally, we have our function sine x plus cosine x on the intervals 0 to 2 pi. So let's take a look at this one. Oh, and actually, before we do, let's verify that it meets the hypotheses. Is this a continuous function? So think about that. Okay, you should say, absolutely it is. And why is that? Because these are trig functions, and trig functions are continuous wherever they're defined. We learned that before. And the sum of two continuous functions is always a continuous function. So therefore, this is a continuous function. So we can use this test. Okay, so let's go ahead and take a closer look at this function. We need to compute its first derivative. And to find the critical numbers, we'll look to see where this is 0 or undefined. Well, it's not undefined anywhere. These functions are defined everywhere, so their difference is defined everywhere. But it might be 0 somewhere, so let's set up that equation. And when we solve this, what did we do last time? We added sine x to both sides. And then we divided both sides by cosine x. And then we realized that this is just the equation 1 equals tangent x. And as we discussed in the last video, I'm not going to go through it in detail here, the two solutions to this equation on this interval are the values pi over 4 and 5 pi over 4. Those are our critical numbers. Those are the things that are making f prime equal to 0. Now, it's important to keep in mind that there are actually an infinite number of values x for which this is 0. But we're only looking for the values in this interval because that's what we were told up here. Okay, so our critical numbers allow us to, just as before, break up the number line. And here we're looking from 0 to 2 pi and into regions here. Okay, and so we'll just investigate the sign of f prime in these regions. Okay, so in this region, plug in a number like we did in the last video, pi over 6. And we saw that if you plug pi over 6 in here, you get something positive. And if you plug in something in this interval like pi, you get cosine of pi is -1 and sine of pi is 0. So -1 minus 0 is -1. It's negative. I think we plugged 3 pi over 2. We observed that that was in this interval. Plug that in here. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. 0 minus -1 is +1. It's positive. Okay? And so that's what we're seeing. We see that the derivative changes from positive to negative at pi over 4. So positive to negative means it has a local maximum there. So we have a local maximum here. And what is the value? Well, to find the value of that maximum, we will plug pi over 4 into the original function. Okay? Well, sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. And you add them together, you get root 2. So f has a local maximum value of root 2 at pi over 4. And what happens at 5 pi over 4? Well, let's see. F prime went from negative to positive. So that corresponds to a local minimum. And what is the value of that local minimum? Well, plug 5 pi over 4 in to these functions here. Sine of 5 pi over 4 is negative root 2 over 2. Cosine of 5 pi over 4 is negative root 2 over 2. Add those together, you get negative root 2. So f has a local minimum of negative root 2 at 5 pi over 4. And there we have answered, and so here we have answered the question. Okay, so let's take a look at the graph just to verify that things look okay. Here's the graph, and now where's our local maximum? Right here, right? And that happens at pi over 4. And the height of the graph, sure enough, it's this is 1.414. That's square root of 2. That's square root of 2 is 1.414, and it keeps going. This is an approximation, right? So that looks right. And we have a local minimum over here. That happens at 5 pi over 4. And the value of the function there is negative root 2. So matches exactly what we found. Okay, so that's using the first derivative test to find local maxes and local mins of functions. And you should keep in mind, I kept going back to that theorem and looking at it, the first derivative test, but you really should just make intuitive sense. If you're thinking about a function that is has a local max, it has to be increasing and then decreasing. So the derivative has to be positive and then negative, right? So just in your mind, even without memorizing that theorem, a positive to negative derivative means local max. And if you have a local min, that means it was decreasing and now it's increasing. So the derivative must have been negative and now it's positive. So negative to positive derivative means local minimum. So, you know, once you know this, you don't really need to memorize that theorem. You just, now that you know that that theorem exists, just think intuitively, what has to be happening if you have a local max or a local min? What has to be happening with the derivative? And just check that that thing is happening. Anyway, I hope you learned something here, and I'll catch you in the next video.